Hi guys. Hopefully everyone can hear me at the back of the room. I'm not always very easy to hear. Can somebody at the back raise their hand if they can hear me okay? All right, excellent, great. All right, so I have a number of slides here, but I'm going to try and keep the presentation moving so that we have some time for questions at the end. But there is a lot of material to talk about, so. Using open source telemetry to drive change in management environments. Just a quick bio for me. As was mentioned, I work for the Office of the CTO at Dell EMC. I've been in Octo for about 2 years now, and my main focus has actually been management and orchestration. And as part of that, we've been looking at ways to leverage telemetry and start to think more about the orchestration side of management and orchestration, and ways to do more data-driven orchestration and automation, right? So-called kind of closed-loop automation, or if you're familiar with control theory, along those lines. So enough about me. Let's move into the topic, what we're going to cover. So at the end of the presentation, what you'll have is a sense of the data collection architectures that are available to you for collecting and publishing telemetry, and a sense of how that telemetry can be leveraged, right, as part of an automation solution in particular, but we'll talk about some other use cases for telemetry as well. So we're really going to examine some paradigms, right? So we're not going to do a deep dive on statistics or big data, but we'll certainly kind of allude to some big data techniques that can be used to pre-process data to make it amenable for automation or amenable for visualization for operators, right? So we're still kind of leaving operators in the equation here. In particular, at the end of the presentation, what I hope you have is a sense of how to leverage telemetry to drive value. By value, I mean to be able to demonstrate value through automation. So, again, sort of in the loop or life cycle theme, at the end of the presentation, what I hope you have is a sense of how to ingest telemetry, how to prepare it, how to use it to drive automation solutions, and then how to be able to demonstrate back to your own business units the value of consuming telemetry in that way, right? And as with everything in technology, this is a journey. So what we'll talk about at the end of the presentation is what paradigms you should be thinking about depending on where you are in that automation and telemetry collection journey, right? So quick general definition of telemetry. I think that, like a lot of words in technology, the term telemetry is overused. I thought a quick industry definition would be useful, then we'll talk about the definition that we're going to apply here. So this is literally taken from the dictionary, right? The process, telemetry collection, I would say, is the process of using special equipment to take measurements of something, right? From an industry perspective, that could be pressure, speed, temperature, medical readings. If we're talking about something like the SpaceX program, it could be telemetry that's used not just for the purposes of data collection, but also control, right? So it might involve telemetry about attitude, right, of the Falcon 9 rocket, for example. And telemetry that we can use. I want you to sort of start to think about telemetry as something that's not just about data collection, but ways that we can consume that data for control purposes, right? So I think that, to look at this industry definition kind of drives that. One of the things to take from this too is this idea of discrete sensors. And I think this is where sort of the system definition of telemetry departs from the industry definition maybe a little bit, although I'm kind of advocating for a paradigm here. So when we talk about system telemetry, we're talking about using really a technology architecture that can collect information in the form of measurements and statistical data, right? So similar to what we were just talking about from an industry perspective, and then forward it to a set of centralized systems of processing, right? And that might not just be over a radio network, that might be over a digital network, but the idea is that we're using discrete sensors. I think when we talk about system telemetry, we should think about those not just as being hardware sensors, but really discrete, isolated components. They could be services, right, running on an infrastructure that are collecting discrete data, forwarding that data over some transmission medium to a set of centralized systems that are going to process that data. And some of the architectures that we're going to look at in the context of this presentation, that collection process processing process, which is alluded to here as well, and publishing process is actually performed in a distributed fashion on the node, right? So whereas in the industry definition, we think of data collection being done by sort of sensors forwarded to the cloud, where processing is done from a systems perspective. When we look at some of the available system telemetry platforms, that processing and publishing actually occurs on node, right, for example. And then obviously with the emergence of big data, the idea of telemetry collection feeds into this sense of being able to collect data, unstructured data, a variety of data, correlate that, and then use that to produce actionable intelligence. So when we use the term actionable intelligence here, we're referring to data we can use, right? I've been in the system space for a long time, and I've seen a lot of organizations collecting data that they're not really leveraging, right? You can collect large volumes of data that you don't do anything with, right? So we'll talk a little bit here about how to think about making telemetry actionable, right? So what is a system telemetry framework? So this diagram illustrates, it could be a general framework for any of the particular paradigms that we're going to talk about here, but what it shows again is this idea of discrete sensors or services running on an infrastructure at all levels in the stack. We think of a telemetry life cycle as being about collection, processing, publishing, and then using that published data to drive some form of action, right, where that might be visualization of that data. And again, that visualization still needs to be useful to an operator. It might be about driving automation. It could be about machine learning, building a knowledge base of facts that you then use to drive learning and further insights. Or it could be about analysis that goes back to the business, right? In the middle, I've introduced some terms, and we'll talk about these. Again, not a big data presentation, but we'll drill down on some of these terms. I've deliberately tried to steer clear of delving into the math too much and instead kind of present conceptually what these terms mean, just to give a sense of what we mean when we talk about processing, and also what are some of the things you could do through some of these telemetry frameworks by way of processing before you forward this data, for example, to a big data store for analysis, right? When does it make sense to do that processing on network versus, or on node versus at the data store itself. So what constitutes telemetry data? Really anything, right? Anything that you can use that is informative, that can be correlated in a way that's informative up and down the entire stack, right? So anything that can be measured, certainly, right? But anything also that can be correlated to drive insights. So what we're representing here is hardware data like system event log data, smart data from SSD drives, disk drives, for example, certainly OS data, event tracking information, going up the stack all the way to the application, runtime, trace information, vendor product data information, environmental data, power data, etc. Right? All of this data potentially has value if we can correlate it and process it in a way that makes this data actionable. Network data as well. Increasingly, we're starting to see technologies emerge that build topology of your network. We'll talk about how to lend context to telemetry in a second. And then how to leverage that data, correlating it with compute and application and service data to do some interesting stuff. So what makes telemetry actionable? And again, I know this is a general slide, but what I'm trying to do here is kind of build a framework that you guys can hang some of the details on. You can go off and do research on some of these terms, on some of the available statistical sites, and drill down on what they mean from a mathematical standpoint. So history, obviously, is useful. We'll look at some examples of that in a second. Context, right? Context could be tagging events with resource IDs, so that we can pinpoint where events are occurring across our infrastructure or across our application space. Normalization, and I give some examples of normalization a little further into the presentation, but basically normalizing data in a way that allows us to be able to identify unusual events, outliers, right? Sometimes in a way that allows us to be able to identify outliers that indicate our data isn't valid, right? Validation, obviously, again, we have to be able to validate that the data that we're ingesting is accurate. Real-time fidelity, meaning up to the minute, right? If I'm going to leverage telemetry to drive orchestration, then I want an up-to-date picture of what's occurring on my infrastructure, right? And this becomes increasingly important as we look at scale in the data center, and we look at orchestration at scale, right? Where many things could be changing as we're orchestrating, standing up an application, for example, and its associated configuration. And then knowledge creation, the ability to be able to use the data that we've collected to drive models that allow us to gain new insights and allow us to be able to start to drive in the direction of things like machine learning. Right? So if we are able to kind of instrument telemetry in this way, we make it infinitely more actionable from the perspective of automation and much more actionable from an operator perspective, right? How many of us have looked at volumes of data, right, in an operator dashboard and kind of scratched our heads, right? So, I'm a big believer in dashboards should do some of the visualization for you. Right? Should help to highlight events that are unusual, right? Even just for the process of you being able to learn about your own system and kind of baseline your own system. So what techniques do we use to process telemetry data, and what does this mean from sort of an actionable perspective? Well, so normalization, in general terms, in kind of layman's terms, you can think of normalization as being the process of kind of disambiguating data, right, to eliminate redundancy, certainly, to make sure that the dependencies that we reflect between data elements are logical and that they're also proportional, right, which can help us when we get to the point where we're analyzing data, right? So if you think about what allows us to be able to take raw telemetry and turn it into something that we can execute against through automation, we have to be able to analyze that. There has to be a decision-making capability, right? And that decision-making capability needs data that is normalized, it's proportional, it's accurate, in order to come up with the right conclusion and then drive an execution. So when we talk about normalization, again, these are terms that you can drill down on. We think about things such as filtering, right? Filtering out elements either that we don't want to look at or not relevant to the problem that we're trying to execute against or are inaccurate. Normalization from kind of a min-max perspective, decimal scaling, and then standard deviation, right? And as we talk about some of the frameworks at the end of this presentation, some of these frameworks, for example, Intel Snap will do some of these statistical disambiguation for you, right? So we're not just talking about what you can do from a data store perspective, but we're talking about how you might be able to pre-process data to get it ready for ingestion. So, so this slide talked to normalization techniques. This slide talks to, okay, having normalized my data, what does that mean? What does that do to the data that makes it actionable, right? So we have an example here of time series averaging. We can't really do averaging of data until we've normalized that data in a way that makes sense. Averaging, really, if you think about it, is the process of taking sort of a bounded set, averaging that using either a mean or median, for example, moving averages, so that we can reflect things like the last 15 minutes of activity, right, against a data store, for example, or perhaps look at consumption patterns, right, for across an infrastructure from, say, a public cloud, private cloud, on-premise perspective. So this takes raw data and turns it into something that's actionable in the sense that we could, present this data to our business owners. It has value from that perspective, but it also could be used to create a history that's useful for driving automation. Another thing that we can do once we've normalized data is to identify outliers and unusual patterns of behavior. Right? And we can do this in a statistical way that doesn't just depend on an operator's eye to identify that something looks unusual, right, from sort of a baseline perspective. So here's an example of being able to correlate network latency to CPU contention. It's actually a virtual machine example. If any of you are familiar with virtual machines and the CPU ready time statistic, in particular from a VMware perspective, being able to correlate CPU ready time to network latency might tell me that I have an unusual amount of network load on a particular cluster or a particular set of hosts that's impacting virtual machine network latency, potentially impacting an application, right? So these are two disparate metrics. Then when we correlate them in the right way, take on new meaning, right? So that here what we're looking at is sort of an outliers chart that shows, ideal traffic pattern and CPU CPU ready time values, and then something that indicates contention. So what other techniques can we use to process telemetry data? Well, decoration is another technique that we can take advantage of. What do we mean by decoration? And so this is something else that you can do through some of the available telemetry processing frameworks. So we can decorate data in a way that provides context, right? We can decorate events in a way that tells us, where that event was generated on the infrastructure. Right? Was it generated from a particular chassis, rack, compute node, network element? And then if we can tag metrics in that way, we can start to correlate them. We can do analysis to correlate them to start to visualize what's happening. And that can help in doing things like root cause analysis, for example. Right, so we have an example here of correlating CPU utilization that's occurring on a particular CPU core with a particular node, with a chassis, with a rack ID, and a particular data center. And obviously, if we're seeing high CPU measured in megahertz on more than one node or in a particular cluster, that tells us something, right? And the action that comes out of that will be very different than if we're seeing CPU contention on a single CPU core. So how does decoration assist us in producing actionable data? So here's an example. It obviously looks very much what it is, a directed graph, right? But that doesn't mean that you have to dump this kind of data into a graph database. There are other ways to sort of visualize this type of data. But graphs tend to lend themselves to visualizing related elements. So that's pick this particular model for this example. So here we have an example of root cause analysis, where having that additional context can allow us to see how a set of elements have been affected by a particular event, in this case, the failure of a particular physical disk. Right, so we can see the RAID group that's affected the storage volume, that it's affected a particular node, and therefore the containers that are running on that node. And based on this information, we can either take the appropriate action as an operator, or we can kick off an orchestration to address the issue. Right, so this lends color in terms of things like fault domains, performance domains, additional information that we need to inject in order for either an operator or a system, like a decision engine, to make a decision about what's the appropriate course of action to remediate. Without this kind of context, we potentially perform the wrong action, right, to remediate the situation. So now we're really pushing into data techniques here. We're talking about map reduce and splitting. This example is in here because what we're increasingly seeing, so the presentation is about telemetry and automation. We've kind of separated the two in the discussion. But the truth is what we're starting to see in the M&O space is telemetry and orchestration are starting to come together, right? We have orchestration platforms or management platforms or infrastructure as code platforms like HashiCorp Terraform, for example, that ingest state data and other types of data that we consider telemetry, right, in order to be able to drive automation. And then we have telemetry platforms like Intel Snap that are part of this bigger vision that Intel has about leveraging telemetry to drive orchestration. But they've started off in the telemetry arena. Right? So when people say telemetry is kind of, sort of a yawn topic, to me, it's extremely, what you can do with telemetry is extremely interesting if you can instrument it in the right way. Right? So here we have an example of analyzing events, being able to process a large number of events in a rapid fashion, in a distributed fashion, using MapReduce, in order to be able to quickly identify, for example, how many events are occurring on a particular rack or chassis, and how many events of a particular type are occurring. Right? There are other ways we could process this data. So if any of you are familiar with MapReduce, there are benefits to MapReduce. It's not ideal for every problem that is out there. But this is just an example. So I think there's something missing on this slide, but really what we're showing on this slide is an event-driven environment, right? So I mentioned a second ago that we're starting to push into this world where that loop between telemetry collection, being able to action something from that, make a decision off that telemetry, right, and then action something is getting tighter, and vendors are starting to look at this space from different angles. Ultimately, the ultimate expression of this is being able to ingest a large amount of events off of an infrastructure, right, and then correlate that data in a way that allows us to be able to make a decision. So what we're illustrating here is, it's a little disjoint maybe to this example, but I'll tie them together, right? So I mentioned a minute ago that in order for us to be able to action something on an infrastructure, what we need is really up to the millisecond expression of the state of that infrastructure, especially when we start to get into scale, right? If you imagine executing, the installation of an application that's going to sit on, let's say 100 or so nodes on an infrastructure, compute nodes, right? Maybe it's a data analytics task that you're trying to distribute. It's an ephemeral task for one thing, right? And orchestrating against that number of nodes, when you actually kick off that orchestration to provision those nodes, there's a high degree of probability that the state of some of those nodes is going to change while you're running that orchestration, especially if you're not the only orchestrator in the environment. So what we want to be able to do is to have a completely accurate picture of what's happening now on that infrastructure as we run that orchestration. One of the ways that we can piece that together is to take advantage of a technique that's called event sourcing. And what event sourcing allows us to be able to do is to literally, as we execute a task, so here we have an example on the left-hand side of the process of provisioning a KVM compute node. So starting with discovery, we are kicking off a Pixie boot task, right, to do some initial tooling of that node, perhaps to install drivers, or maybe to do discovery, catalog what that node is, what devices that compute node has. Then we're doing a firmware update, and then finally we're installing an operating system, actually a hypervisor, KVM. Right? At each one of those tasks, as we complete or fail at that task, we're triggering an event. And if we take those events and we capture them to an event store, then in order to get a picture of what's occurred and the current state of that compute node, we can literally replay those events to get the current state. Now that has value for a couple of reasons. One of the reasons it has value is it provides us with a history of what's occurred on that node. And it also gives us the ability to be able to essentially play back these events in order to reconstruct the current state of that node. Where MapReduce comes into play potentially with this, it's not reflected on the slide, but if you look at the right-hand side of the slide, we're depicting a presentation layer and a question, right? Is there an available KVM host that I can build a virtual machine on, right? So this host that's just been provisioned as a candidate, maybe one among many, and what we should be able to do in order to answer this query or question is quickly reconstruct the state of this KVM node, right, by replaying the events. MapReduce is one technique that we could use against the depicted event store, right, that's capturing this list of events against that resource ID in order to be able to quickly return an answer to that question. So there's the connection, not depicted on the slide, and I apologize, but that's the connection to the previous slide. Okay, so moving along here more into sort of the automation portion of the story. So we've talked a little bit about sort of how to pre-process some of your data from a conceptual standpoint to make it actionable. We've talked about, a little bit alluded to some types or paradigms, automation paradigms that can leverage these different types of data. So what we're talking about, obviously, is this loop that I've already alluded to, right? So let's talk a little bit about the automation side of the equation. So we talked about preparing telemetry. What do we need on the automation side, on the orchestration side, in order to be able to realize change from telemetry data? So this is abstract. It doesn't represent a particular architecture almost deliberately, but there are, if you think about even some of the presentations you've seen this week, right, there are management and orchestration platforms that you could fit into this model. I give some examples of them on the slide that follows. So if we want to be able to drive automation through the collection of intelligence, right, the collection of system telemetry, then we need a declarative interface, right? What we mean by declarative in this context is an interface that allows me to express the requirements, the configuration requirements, for example, for an application. Whereby the system can then interpret those configuration requirements and then execute an orchestration. Right? The reason that declarative interface or configuration interface is, think of it as a manifest, right, that expresses the requirements for a particular application. The reason that that's significant is it makes an automation system amenable to other systems. It can be a system submitting the request, right? If I can reduce what kicks off a whole automation to a manifest that describes a set of configuration requirements, and I can use something like Terraform, for example, that follows this paradigm to actually execute that request, and then I can have a system potentially that issues that request, right? Or an operator, but potentially a system. So what we've depicted is that declarative config. These are elements that are important to have sort of control type automation, right? Closed loop automation driven by data. Business and domain logic is a bit of a euphemism here, sort of glossing over something that's actually quite complex. But it really gets to generally gets to things like rules engines and being able to abstract logic outside of code in a way that allows an operator or possibly a system, but an operator to go in and describe some rules of the road, guardrails, if you like, for the system. And if we're going to do full automation, then operators obviously want to have some control over that automation. And one of the means of control could be through the expression of business logic, right? That says, for example, if you see high memory and compute utilization on my cluster, on my OpenStack cluster, for example, you can go and scale and add additional nodes to the cluster if that's merited, but don't scale beyond this number of nodes because I'm paying for these nodes and I don't want to exceed, 8 nodes per cluster, either for performance reasons, fault domain reasons, or because of cost. Logic like that needs to operate, rules-driven logic needs to operate from a fact base, right? And although that's shown here as a single block, in reality, that fact base is going to consist of data models and databases that collect the type of information we were just talking about, topology data, right? Context, time series data, right? Perhaps in a key value store. Anything that can provide context as the basis for making a decision, right? So that business and domain logic is our decision maker. It's going to decide, does a rule apply, does it not? Has an SLO, service level objective, been violated or not? Should we execute a remediation? That kind of stuff. Identity management, I'm not going to get into in detail here, but obviously what we're depicting here is kind of a distributed system composed of discrete components. And each of these discrete components that are exchanging information to drive automation, those conversations need to be secured in some way. Service systems and users need to be able to identify themselves to a system. And we also need guardrails from a tenancy perspective that don't allow, in a shared environment, in a cloud environment, one tenant to impinge on the resources of another tenant. Real-time intelligence gets to what we were just talking about. So you can see here I'm alluding to telemetry data, which we described as anything that can be measured, anything that can be instrumented. An inventory and service registry is what we might have called in the past a service catalog, right? And if you go back like 5 or so years, and you think about where we were from a cloud perspective, almost everybody's cloud had a catalog interface, right, that represented their cloud offerings that could be used to drive automation. When we're talking about the type of world that's depicted here, we don't necessarily know, right, in a sort of prescriptive fashion, what is the automation request that's coming into the system. Right? We don't know, especially if it's driven by a system, and depending on the capabilities of the system, we may not be able to predict up front in a way that allows us to kind of provide a prescriptive catalog entry, what it is that the user is trying to execute. One of the things that I worked on before joining Octo was the development of a private cloud for EMC's own development and test engineers. And one of the biggest challenges we had, and this is going back 5, 6, 7 years, was developing a catalog that hit that user base. Because here we have a set of engineers that are really probing edge cases in product, and almost invariably when we stood up a catalog entry, what they would say to us is, that's very nice, and that catalog entry that you have there, that probably gets me 80% of the way to being able to build my self-service lab environment, but it still leaves me with 20% work to do, and so therefore it doesn't have as much value to me as it could. Right? So there's a class of users where we don't necessarily know what it is they're trying to test. It might be an edge case, something that we wouldn't think of. Can't really capture them through a catalog. And so on that team, what we decided to do was instead provide them with the starts of an automation framework, right, where they could leverage the automation they already had, really started moving the DevOps direction, right, everything that you guys have been hearing about this week. So when we talk about automation and creating an automation system that can be data-driven, we don't know the data coming in. We don't know what that's going to tell us. And we don't necessarily know in a prescriptive way. We obviously have to have templates for automation tasks, but we don't necessarily know what the workflow looks like up front. Right? So what that says is, what we need is service components. We need inventory capabilities, hardware capabilities, and infrastructure capabilities that we can catalog, that we can advertise, where our incoming declarative request might be, I have this application, and it has these requirements. It may be very specific, or it might be, I have this application of this type, and it has these service level requirements. Go figure it out. So in that kind of environment, we want to be able to do some of what we were just talking about, tagging, right? Perhaps tagging hardware capabilities with SLO data, service level objective data, so we can say, this is our gold compute service. It's kind of not a very good analogy, but I know everyone's familiar with kind of the gold, silver, bronze paradigm. It's not perfect, but you guys know what it is. So, we could tag resources with those kinds of SLOs, right, in order to support the selection of a resource in the service of an application. Okay, so on the task automation side, it's interesting. The task automation is not easy, but there's a world of, as you'll see on the next slide, automation tools that you can use to orchestrate tasks in your environment. You guys have a lot of them already in your data center, right? That's not so much the challenge. It's more going from deciding what needs to be done to using an orchestrator that can compose what needs to be done, right? Compose the overall workflow and the set of tasks that need to be orchestrated, and then actually executing that through Ansible, Chef, Puppet, Terraform. Terraform actually would probably put more in the class of an orchestrator, right? But there are plenty of automation tools out there, and any of them you can use. And then something else to think about in sort of an automated environment is test and simulation, right? How do you, that goes beyond sort of test and validation to being able to simulate what's the effect of executing something on the infrastructure, right? What's the effect of changing this rule in the system? What's that going to do? Being able to predict the effect or trace the effect of an automation on the infrastructure, to understand the conflict between different automations in the environment, for example. Global resource management, again, is a little bit of a euphemism here. It really talks to some of what's starting to emerge. So part of what I'm trying to give you here is kind of a pattern for understanding different technologies in the space, right? Think of it sort of as a map to be able to identify what sort of elements you need to be able to put together to construct automation, right? And to reinforce that as much as some of these technologies are still emerging, there are technologies out there that you can start to become familiar with today that you can leverage in your own environments. And so in the global resource management space, you have many tools out there that are trying to solve the problem of how do you execute tasks on an infrastructure in a more abstract fashion. How do you leverage things like Mesos, for example, as a way of consuming resources in the environment and providing those to applications that need resources, right? So there are many vendors, many open source tools that are starting to tackle this problem. And if you understand where these technologies fit, you can start to experiment with some of them. Because again, I don't know the problem spaces that you guys are looking at. Maybe when I leave enough time here and you ask some questions, you can tell me. All right, so this is a bit of an adaptation of a slide that I liked that I found online by a gentleman by the name of Kevin Fishner from HashiCorp. I know HashiCorp have been here, Rachel has been here this week. And I liked it because it kind of put the different tools in context. It's not perfect. You could argue some of the categories, but I think they're useful. If you go looking for Kevin's name and these terms online, what you'll find is he describes for each of these types of automation and orchestration frameworks and tools, where they fit from an immutable infrastructure, config management, or virtualization perspective. And then for each tool, he talks about what they lend from a management, tooling, and infrastructure perspective, because all three of those things are important when we talk about automation, right? When we talk about infrastructure, we think about things like software-defined infrastructure, right? How accessible is that infrastructure to being automated through an API? Tooling, we think about configuration management tools like SaltStack or Ansible, been in this space for a while. But really, at each one of these layers, you'll find elements of management, tooling, and infrastructure. And the management is starting to put some intelligence right behind tooling and infrastructure to be able to do some interesting things from an automation perspective. We doing on time? 5 minutes? Okay.
5 minutes and no questions.
Okay, all right, so we'll speed them. I'm sorry. Yeah, so what I would say to you guys is if we have some time in the room afterwards, I can make myself available for questions, or outside I can. So let's speed through the rest of my slides here. What types of telemetry architectures do we have that exist? And I've got some examples at the end of the deck. I'll also make sure if you look up my Twitter handle, I'll put it up again at the end of the presentation, that you can get this presentation online and drill down on it. But there are sort of three general types of telemetry architectures that are starting to emanate, right? First is telemetry architectures. I think of OpenStack Ceilometer when I think of the slide, and I have some details on Ceilometer, right, which is started off as a virtualization platform with some robust management capabilities and API-driven capabilities, and has started through the Ceilometer project to provide the ability to be able to collect data, diverse data from an OpenStack environment, and then publish that data either to the cloud, to a data store, to data streams for ingestion by other analytics tools. So this is sort of the OpenStack Ceilometer model, right? Processing is done centrally through components like Ceilometer, Noki, AODH, right? Noki is Ceilometer's metrics collection capability. AODH provides a notification alarms capability. This type of architecture, I think of Intel Snap, right? I alluded to telemetry platforms that allow you to be able to ingest telemetry, collect telemetry on node, process that telemetry, and then publish that telemetry to the cloud. So here's an example of a distributed architecture. There are a large number of collectors already that are available for Intel Snap. And, again, Intel's starting to think about automation in this space as well, but they've started in the telemetry space. And the appeal of this is the number of collectors, the fact that it's agnostic from a platform perspective, and it has collectors that go all the way up to the application and down to hardware. But that you can also distribute collection, processing, and publishing activities before you publish the data to a data store or a data stream. And then finally, kind of the model that we're driving towards, and I think this is where some of the IoT middleware frameworks start to become interesting. is that idea of discrete sensors, services in the environment collecting data, publishing that data right to a gateway, being able to use the middleware framework to do processing and publishing of that data, and then publish, ultimately publish that data to external data services or proprietary data services for analytics and consumption. Right? And we're also showing here again the idea of this entire loop, right? Collect data from the platform, like event data, state data, analyze that data, use that data to drive changes on the platform. Okay, so here we have some details on Ceilometer. We've got like a couple of minutes left here. Right, so Noki, AODH, Panko. The slide deck focuses mostly on Noki and AODH. So this is the architecture. What you can see here is the collection architecture is separated from the transformation or processing process in Ceilometer and publishing, right? That's all done centrally. And part of what Noki, if you do some reading online, was intended to address is some prior kind of performance issues in leveraging Ceilometer for data collection. Noki is actually a standalone service that you can leverage, not just an OpenStack environment, right? So open source vendors are starting to get the message of being able to create discrete services that can be consumed in different ways. Can you drive with this data? So in this case, if you're using if you have an OpenStack environment, you can leverage Ceilometer to drive heat orchestration. So for example, in response to high CPU utilization on a set of nodes, I could use heat to scale out to an additional set of nodes to address the issue if that's the appropriate course of action. Obviously here we're kind of skipping over a whole bunch of logic around whether or not that's the right thing to do, right? That gets to some of the context and decision-making capabilities we were talking about earlier. For each of these examples, if you take a look at the slide, I've detailed what the pipeline, how we actually create that collect, process, publish pipeline in the particular telemetry solution. So that's what's illustrated here. One of the nice things about Noki is you can actually publish data directly to Grafana or Horizon for visualization. And then I've used Intel Snap here as an example of being able to create and consume data in a way that provides context and normalizes that data to make it useful for analysis and for driving change on a system. Right, so we have an example here of a Snap data flow. I think are we out of time? Okay, all right, so I'm going to have to wrap. I apologize, guys, there's a lot of material to get through here. What I will do is, can I hang out for 5 minutes for questions? Okay.
They just get to be late for lunch.
Okay, so it's up to you guys whether or not you're more interested in telemetry collection or lunch. I suspect lunch is going to win, but in the event it doesn't, I'll be up front if you guys have some questions.
You have an hour and a half to go get lunch, so stay here.
Okay. So do I?
You can take. We have extra time on the last day typically.
Yes.
Okay. So all right. So I'll keep going. Good. You guys, you're feeding my my bad behavior and running over time. All right, so this example, so I'll slow down a little bit. This example is an Intel Snap data flow example. It demonstrates on the left-hand side the large number of collectors that are available for Snap, as well as the processors that are available. In this case, Snap has a particular processor that supports anomaly detection, right? So these are processors think of as being able to do tasks like filtering, averaging, identifying outliers, statistical operations. Right, so you can look online at the open source project for details on what the types of tasks the processors can perform. In this case, I've presented an example where we have a disk read issue that's occurring, right? We're picking it up at different levels in the stack to the different collectors. So here again, the fact that we're picking this up at the disk level, at the Nova level, in different ways, right? And if we can pick up these events within, say, a certain time window, we can start to identify that they're related, especially if we're able to use, Snap also has a tagging capability, a decorating capability, or processor for that. So now we can not only identify that these events occurred in the same period of time, but we can also identify that they occurred in infrastructure that's related potentially. depending on how we instrument the data. Right? So here illustrating that Snap has a graphite publisher. So these are things that you can leverage that you don't have to build, right? You can certainly build collectors or publishers or processors for Snap, but you can also leverage what's already available. And then this example expands on the previous one a little bit just to show, again, as I was just saying, if we couple the anomaly detection processor with the tagging processor, now we can create some useful data that gives us context to know that these events are related. And what we're illustrating on the right-hand side here is not just using the graphite publisher, but using Kafka, in this case, to populate a fact base. We can call it a fact base of telemetry facts, right? Basically, events on the system, key value pairs, right? With topology facts that we can feed as part of a fact base to a rules engine, right? To start to make a determination on what's the appropriate action. So I'm not saying that you have one solution that does all of this for you. When we get to the action end of this, there are some things that you have to build and integrate yourself. But, again, those roads and bridges that have been down for a while in the full automation story are starting to get populated. So what can we do with this data? Well, if we introduce topology into the data, we can do things like graph visualizations, right? This is just a picture of a random graph in this case, but it gives you the sense of, if this was a infrastructure topology, we could correlate compute nodes with, the storage nodes that are having the issue, start to identify that, we have a disk that's getting unrecoverable read-write errors, and that's causing problems across our infrastructure. And then what can you do with this data? So we can visualize the data. We can execute against this data as well, right? So we could use something like HashiCorp. You'd have to front-end this with something that makes a decision. Not illustrated on this slide. Actually, it is. The rules engine in the center of the slide, right, is going to make a determination. Has a condition been satisfied? That means that we should invoke an action and pass a request to HashiCorp to perform an operation on the infrastructure. Right? Maybe it's provisioning another node. 2 minutes? Okay. So what I would say in general is to think about when you look at these tools, and I gave you 2 examples. There are others. I think this slide deck could probably use an example of sort of complex event processing, but that's a big topic in its own right. Is to think about where you are, not just on your telemetry collection journey, but where you are on your automation journey. Right? Are you already starting to collect some data? Can you start to use some of the telemetry frameworks to process that data to make it actionable? That's a good first step. Can you think about using these telemetry frameworks to process this data in a way that makes it useful from a business perspective? Right? That might lend weight to the argument that you want to do more of this kind of telemetry collection and automation that has value to business, right? In reducing risk, improving efficiency, et cetera, et cetera. Where are you in automating your DevOps lifecycle, right? Is that a piece of the picture here? There are certainly DevOps-type automation frameworks, and I'm not just thinking of things like HashiCorp, but I'm also thinking of development frameworks like Jenkins, for example, that you could tie in here. From a developer perspective, is there a way to tie in automation frameworks that are already being used in your environment as part of this picture? And then, what config management tools are you already using? Do you need to start to look at some of the infrastructure as code platforms that are available? And then, where are you in automating your DevOps lifecycle? So, demonstrating value, these are some of the things I think we have to wrap at this point, but these are some of the things to think about in terms of demonstrating the value of collecting telemetry and processing it, right? Reduction of risk, metering usage, being able to optimize infrastructure footprint, right? Can you get a greater density of VMs or containers onto the footprint that you have, for example? Validation that the processes that you have are working, right? Providing data back to the business that's useful maybe in things like product design or development. Right? And Q&A, which we don't have a lot of time for now. But if we have to, John, you said we...
Could you follow up?
Yeah.
I don't want to go too long, but
yeah.
maybe because we finish here and then do follow-up questions post.
Yeah, we can do it outside if we need to, too. Great. Thank you, guys. Thank you for your attention. Appreciate it. Thank you.